Welcome back to math. Today we are looking at lesson 5.07, which is triangle congruence part 2. So this is the second day of triangle congruence. Be sure you've done the previous lesson before we do this one, because we won't be going over the rules as slowly or as clearly as yesterday. But we're going to be using the same rules as we did yesterday. We're not technically learning anything new today, so that should be a relief. This is mostly a review, and then some additional problems that may be harder than the ones we've looked at so far. So, today's objective is, given a pair of triangles, I will state if the triangles are congruent by SSS, SAS, AAS, or ASA. And you can see I've written in there, or HL, because we missed that one, or not congruent. So we have an idea of what all those acronyms mean, all those letters we've thrown together. So look at these emojis and think, how are you feeling about demonstrating that triangles are congruent? Proving that two triangles are congruent by one of these rules, one of these postulates or theorems. So here are the triangle congruence rules in question. We have SAS, which was side included angle side, SSS, which is side, 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 HL, hypotenuse leg. Now remember, hypotenuse, that's only applicable for right triangles. Only right triangles have a hypotenuse. So HL can only be for a right triangle. ASA is angle included side angle. And then AAS is angle, angle, not included side. So think back. Can you remember which combination of angle side, because we're just mixing up angles and sides here, right? We're putting them in different orders, different numbers of each. Can you remember which ones don't work? Because sometimes it's easier to remember which ones don't work. There are fewer of them. There's only a couple. We remember that AAA does not work because those are dilations, or they can be dilations. So angle, angle, angle does not guarantee the same side length. They might have gotten bigger or smaller, but the angle size remains the same. So AAA is not a valid one. And then the other one we are remembering is SSA, side, side, not included angle. And we kind of remembered that one in a funny way, which was, if you rearrange those letters, that's a bad word, and it's the only one that makes a bad word. And bad words make bad theorems. Bad words make bad theorems, bad postulates, so we can't use that postulate to prove triangle congruence. So we're going to look really quick at GeoGebra today. There's a fun little activity, and I'm going to bring my web browser over here so we can look at GeoGebra. Let's make this window a little bit bigger. Okay, so here in GeoGebra we have some tiles that match these options over here on the side, and you can see these are our triangle congruence rules. That one's invalid, but these are just combinations of different sides and angles. Let's click on the first one here. So we're able to manipulate these. It says click here, and I can click and drag based on these little dots. So what we're trying to do here is we're trying to prove to ourselves that side, side, side definitely does make only one triangle. There's only one triangle we can make with three specific lengths. So notice down here we have a 3, 5, 7 triangle. And what we're going to try to do up here is we have lengths of 3, 5, and 7. We're going to try to make a triangle that is different than that one, that isn't an isometric transformation. Remember what those words mean? It wasn't just moved left or right, up or down. It wasn't flipped. It wasn't rotated. Like it's actually a different size or shape. So let's see. If I drag, that looks like I can kind of make a triangle right about there. But that looks like the exact same triangle I made before, I think. So that seems to be, let me see if I can maybe drag them somewhere else. Maybe I can have them meet over here somewhere. There, looks like they meet there as well. But let's look at this. Is this the same triangle? It looks like it would be reflected, so flipped, and then maybe rotated up. But I still have, like, if I start down here, I can go 3, 5, 7, and 3, 5, 7, and those are all going to be the same angles still. I made the exact same triangle. So I was only able to make those two, really. Those are the only two triangles that are options for me. And so I have to conclude there actually isn't a way to make any other triangle than this one they have here. There's only one triangle I can make, one congruent triangle I can make with these three lengths. So side, side, side guarantees one and only one triangle. That's what we're asking here. Let's skip AAA for just a moment. We'll go to SAS. So we have a side, we have a static side, an included angle, and another static side. And what we have freedom with here is this angle and this side. Can I make it long? Can I make it short? I don't know. Yeah. So that one's pretty easy to show. The only way I can make a triangle here is to put it exactly that length and exactly that angle. And so these match because this is the only triangle I could have made. Once again, side, angle, side guarantees precisely one. There's only one triangle I can make, given two particular sides and one particular included angle. Now let's look at one that we know is not valid. Let's look at AAA. So here we have AAA. We can click here. We can manipulate this triangle. And it's really easy to see these are definitely not congruent, right? Like this triangle is enormous compared to this littler one. But they still have the same angles, right? 30, 100, 50. They all have the same angles. So angle, angle, angle is only guarantees that the objects are what we call similar, or that they are dilations of one another. It does not guarantee strict congruence, which requires all the lengths be the same as well. So we're going to look at the other one that doesn't work, and I'll put this link in the content so you can go play with these yourself. You could go through all the rest of them, but we're not going to go through the rest of them on this video. SSA is the other one that doesn't work. And I think it's neat to see why it doesn't work. So SSA, here we have a static side, and a static angle, right? So here is our static side is 6, our static side length is 11, and then our static angle is 25. And this is just a pretend line that we need to match up with to make a triangle. That'll make that 25 degrees. So our freedom here is this angle right here, and then this length of this bottom segment. So this one seems pretty obvious. I can make a triangle like that. That matches the one up here. But I can also do this triangle. That is a valid triangle, right? 6, 11. But now this side is very clearly shorter than this side. So we have side-side angle. That did not guarantee one triangle. It has two different options, and we can't know which one it is. So this one is congruent. This one is not congruent. And this rule overall cannot guarantee congruence. It might indicate a suspicion. We might look at other sides or other angles to figure out if it is, but it does not guarantee congruence. It could be this other smaller triangle, or it could be congruent. So that's everything with GeoGebra for today. Let's get back to our presentation. Let's get back to our problem solving. We're going to look at a method of solving problems, particularly problems that have a side in common. So you'll see these fairly frequently. So this one asks, well, it actually doesn't have a question listed, does it? But we are going to ask, are these two triangles congruent? The triangle on the left and the triangle on the right. They look sort of like they're flipped over. They look congruent, but we need to prove that they are. We need to use a triangle congruence rule to demonstrate that they actually are. So one of the things I like to do, I think is really helpful, is to draw these separately. Now there's no reason we can't pull these apart, right, and just draw the triangle separately. And that may help us to see the triangles better. So basically the idea is we're just going to, let's see, let me get my line here. Let's see, maybe I can draw it up here. Maybe we can see this. Nah, that one's not going to work. Maybe I'll just draw with the pencil. All right, you'll have to tolerate my scribbly lines because I can't necessarily draw straight lines, but it'll be fine. See, scribbly lines. Okay, so I have a triangle that looks kind of like that, and a triangle that looks kind of like that. Sorry about my scribbly lines. And we have D, A, B here, and D, B, C here. All we did was we took these two triangles and we pushed them apart. And now we need to mark the other things that are marked here. So these lines both had a tick, and then these were both right angles. And then there's one other critical thing we need to mark here, and that is this line right in the middle is congruent to itself. That might seem obvious, right? The length of a line is the same as the length of that same line. Yeah. But what we should do here is we should give it its own mark. If it's a shared side, we'll give it its own mark. So we'll give it 2 tick marks in this case. And now we put that over on our little diagram where we've pulled it apart. And now it's a lot easier to see, right? Now we can just read these off. Side, angle, side. Matches, side, angle, side. So now we know side, angle, side is our congruence rule here. These are congruent triangles, and we used side, angle, side. Now that really obvious thing we just said, a line is equal or congruent to itself, the length of a line is equal to the length of itself, has a fancy name in math because we love to give things fancy names. So this is called the reflexive property. It means that a geographic figure is congruent to itself. So a line segment is congruent to itself. A triangle is congruent to itself. But that also means for these shared sides, we can assume that they are congruent to themselves. So if we split them apart, these will still be congruent to themselves because they represent the same line. Let's look at another example. So are these two triangles congruent? We're talking about this triangle right here and this triangle right here. I know there are several on this diagram. LKJ and MJK. Okay, so I'm going to draw, oh, that one didn't work very well. Let's try a different pen. We're going to draw these triangles separately in order to see them a little bit better. So this will be LKJ, and I'm going to draw this one over here. This one will be MJK. Now we need to move over all of our indicators. We have a single arc and a single arc, a single tick and a single tick. We have 2 arcs here and 2 arcs here. And then we have good old reflexive property, right? This side right here is shared. So we can say these both have 2 ticks on them and are the same. And now we notice they've given us actually a lot of information for these two triangles. They've given us angle, side, angle, side. So we have 4 pieces of information. That's way more than we need. We usually only need 3, right? So we could do angle, side, angle. We could do side, angle, side. Or we could even do angle, angle, non-included side. All of those are valid solutions to this, valid reasons why we can say these are congruent. So we have side, angle, we had angle, side, angle, and we also have angle, angle, side. All of those would work here. Let's look at another one. All right, so this one's for you to do. Pause the video, give it a try. See what you come up with. See if you come up with the same answer I do. So this one isn't too hard to see separately. We could draw these. We could split them out at C if we wanted to, if we wanted them not to touch, but they are pretty easy to see. They're not super overlapping. So we have this side has a single tick, then a common angle, and then another single tick. So side, angle, side, side, angle, side. So we just say those out loud in the order, and we get side, angle, side. These are congruent by side, angle, side. All right, here's another one for you. And so pause the video, but keep in mind, this one is a little bit tricky. It will try to trick you. Okay, so let's look at what we have here. I'm going to draw this one separately because I think it's a little less confusing if they're not smacked together like that. So I'll draw a triangle kind of like that, and a triangle kind of like that. So this will be T, S, and U, and then here we have S, U, and R. Now we move over our indicators, our single arc, there and there, and then a tick here and here. And remember our good old reflexive property. We can put 2 ticks on that shared side, which makes 2 ticks here and 2 ticks here. So now we do have 3 pieces, which may give us a triangle congruence theorem or postulate, may give us a rule that we can use, but we have to make sure it's the right one. Let's look. So we have a side that's in common, we have another side that's in common, and then we have an angle that is not between them. This is the angle that's between them. So this is the angle outside of them, one of the angles outside. So we have side, side, not included angle. Right? SSA. Is that a valid triangle congruence rule? No, no it isn't. And that is the only information we're given here. So it's really tempting. It's very tempting on this one to look at this one and say, oh, that looks like a right angle. That looks very much like a right angle. Right? This looks like an isosceles triangle. This looks like an altitude, a bisector. But we have to keep in mind that they didn't tell us that it is. They didn't tell us it's a right angle. So we can't assume that it is. All we can assume is what they told us. They told us 2 sides and an angle, which doesn't prove congruence. So we don't have enough info to determine. We cannot say it is definitively congruent. We also can't say it's not congruent. We just don't have enough information to tell. All right, one more for you to do. Pause the video. Take a look at this one. Are these congruent? Why? Now I think side, side, side might be our easiest one to spot right away, right? Side, side, side. It doesn't matter what order they're in. They're all just sides. And this is a shared side, so it's clearly, by the reflexive property, it's congruent to itself. So we have side, 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 side. That one's pretty easy to spot. So in this lesson, another thing we need to do is figure out the congruence statement. Now, when we say triangles are congruent to each other, we need to make sure that the order we put the vertices in correspond to the other triangle. So the corresponding vertex needs to be in the same position when we write them. All right, so first let's figure out, are these two triangles congruent? Can we tell that they are? Well, we have a right angle. We have another angle marked with a single arc down here, so those must be congruent. And then we have a side in common. That side is shared, so we know it's congruent to itself. So we have angle, side, angle, and a matching angle, side, angle. This is the ASA congruence postulate. But now let's figure out which congruence statement is correct. So looks like all of these options start with ABD. So we're going to go ABD. Okay, so the first thing we need to do is figure out which vertex corresponds to A. And I'm going to use a highlighter here and make these a color. So let's see, let's start with green. So A is our first one. A is green, and it's the angle that isn't marked. You see, B has the right angle, D has this little single arc. So it's the angle that isn't marked. Can you see what other angle isn't marked? It is C. C is not marked. So we know that A and C must be corresponding parts. So I'm going to go through all of these options and highlight A and C. A, C, A, C, A, C, and A, C. And I need to make sure these are in the same location in the statement in triangle ABD. So here in this first one, you can see A is in the first position, C is in the third position. First and third do not match, so that one we can eliminate. They're both in the first, and here they're in first and second, so we can eliminate that one too. They don't match. Okay, so let's look at our next vertex. Our next vertex, it's going to be ABD, so B is our next vertex. I'm going to use maybe blue for this one. So B is our vertex, and it's going to be in that triangle ABD. So this is the angle we're looking at here. We need to find out which angle corresponds to this right angle. So we have to find the other right angle. Well, the other right angle is right next to it, right on the same vertex. That's very handy. So B is blue, and we're going to highlight B is blue in the remaining ones. B and B, B and B, and those need to be in the same position too. You can see here, ABD, B is in the second position, but B is in the third position here, so we can eliminate that one. They do match in this one. B and B are both in the middle position. This is the only one left, so this is our answer. ABD is congruent to CBD. All right, so let's look at another one of those. Which postulate, well, this one is actually very similar to the one we just did. Let's do this one. Which postulate proves that these two triangles are congruent, and which congruence statement is correct? So again, this is another one that's pretty easy to spot. We have a side in common, and we just have side, 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 right? Side, side, side. But now we need to say which congruent statement is correct. Which triangles are congruent here? So QSP is our initial one. Maybe I'll just start with Q. And let's see, what do we know here? QS is a length, SP is a length, and QP is a length. So I'm going to highlight the things that I know with different colors. So actually, that's probably kind of a thick line. Let's make that thinner. QS, I'm going to make in blue. And SP, I'm going to do in purple. And then PQ in yellow. Well, this blue one has 2 tick marks, so I know that it needs to have 2 tick marks in the other triangle. So let's highlight that one blue. And then this has a single tick mark. This has a single tick mark, and this one does as well, so we can highlight that. So those are what our two congruent triangles would be highlighted. Let's see what those matching vertices would be. So we start with Q and we go to S because we're doing QSP. That's the option of all of these options over here. QSP. Start at Q, go to S. That follows the blue line. So I'm going to start at Q and go to R. That follows the blue line. Now I could also start at R and go to Q. I'm actually not sure which direction to go yet, but we're going to figure it out. QSP, I need to go blue, purple, yellow. So this side I need to go blue, purple, yellow. Q, R, P. So QRP is our answer here, this one. Let's do one more problem. Here are two triangles. Pause the video, give this one a try. See if you come up with the same answer I do. Which statement is true? Well, let's see. We know by the reflexive property that a line is congruent to itself, so I can draw some tick marks there. And we can show that we have side, side angle, and side, side angle, right? We read these in order. Or you could say angle, side, side if you went that direction. But we'll just say side, side angle, SSA. Now first off, is SSA listed in any of these options? We have AAS, HL, and ASA. So SSA is not even an option here. So that's already suspicious. But let's think about SSA. Oh, that was one of the ones we didn't include. That one does not prove triangle congruence. So the answer is there is not enough information here to determine whether or not these are congruent. We can't prove they are. We also can't prove they aren't. We just don't have enough information. So that's it for today's objective. Given a pair of triangles, I will state if the triangles are congruent by SSS, SAS, AAS, ASA, not congruent, or we also have HL, good old HL. Correctly in 4 out of 5 problems. Think about which one of those best represents you.